Okay, for now we are moving through the sinusoidal alternating current, and we are working with alternative values. The main difference between AC and DC is in mathematics that we are using, because for direct current case, you were using only algebraic functions, only constants, and for alternating case, you are using complex vectors. It is the main difference. All methods, all main laws, and all formulas stays exactly the same, but the difference is only in mathematics. And if for DC you have only resistors, then for AC you have additional coils and capacitor as a representation of electromagnetic field. Generally, for all resistors, you have the Ohm law. For resistor, current equals voltages divided on resistivity. But for coil and capacitor, the formula uses the operation of taking derivative, and that is the first problem that occurs on the alternating current. For coil, voltage equals derivative of current multiplied on inductance, and for capacitor, current equals derivative of voltage multiplied on the capacitance. For resistor, everything stays the same. Just Ohm law as proportion between resistivity. And that is why for direct current, if you have constant values, then for your coil, current constant and the voltage equals 0, because derivative equals 0. And for capacitor, the current equals 0, because also for constant values, derivative equals 0. That is why coil we are describing just as element without resistivity, just as the connecting wire. And for capacitor, we look in it as open circle, as infinity high resistivity. That is why generally we say that in DC we are not interested in coil and capacitors, and we could neglect them in describing of system. That is why in DC we have only resistivities. In AC we have all three elements: consumption and electromagnetic field. And then the simplest way to transform this formula is to move on the complex plane. We are moving on the complex numbers. And as we described on previous lectures, in complex number variables, Ohm law stays the same. And for current capacitor, we are obtaining the most similar with the Ohm law situation. We could also say that we also obtain the Ohm law formula. It looks like imaginary number of resistivity of imaginary resistivity that we point as X for coil and multiply on current. For capacitor, or okay, in this variant of writing, instead of current, we obtain voltage divide over negative resistance of capacitor. And for coil, resistance X equals frequency multiply on inductivity. For capacitor, or let it move just on the whole screen, yeah. It will be omega L, it will be X1 divide on omega C. It is our main formula for alternating current. And if we are using the Ohm law for these three elements in complex numbers with resistivity R, imaginary resistivity J omega L, and imaginary resistivity 1 minus J as 1 over omega C, we will obtain the correct calculation, and we could use all other methods as mesh currents, nodal voltages, and any other methods that we want. It's just a general physical background of difference between alternating current and direct current, and what mathematics are we using in this situation. Just one moment. Here it is. Then, what we stopped on. Previous time we discussed for the sinusoidal variables, the main properties of elements. We discussed that for resistor, current and voltage are sinusoidal, and the most important thing is that these sinusoids lie one between lower than other. This sinusoid have the same phase angle, initial phase angle, and they lies one over other, or one lower than other. And in complex form, instead of this sinusoid, we could draw only vectors with the same initial angle, because this initial angle is the same. And also resistivity independent on frequency, it is a constant value, and the power of resistor just equals Joule heating I square R for the current root mean square value. And the current effective or root mean square value just equals the amplitude value divided on square root of 2. Then for coil, as any magnetic element, as any wire near which we obtain magnetic field, or external magnetic field goes through our wire. Starting from general formula of voltage, we obtain that the difference between sinusoids initial angle on voltage and current equals 90 degrees. And in vector form, it will be that voltage and current with 90 degrees difference between them, and voltage leads this current. For the power formula, we obtain that instantaneous power just in moment of time equals some function, but the average power for the period of time, if we will integrate this instantaneous value on period of time, will equals 0 without any Joule heating. It means that ideal coil doesn't consume electricity. Only resistor consumes electricity. And the same for capacitor. For capacitor, we discussed that starting from the general formula, using derivative between current and voltage, we obtain that also current and voltage sinusoidal functions have difference between initial angles, and this difference also 90 degrees. But in this situation, not voltage, but current leads voltage on 90 degrees. That is mean, if in previous situation voltage leads for coil, then for capacitor voltage lags that these currents, and the angle is minus 90 degrees. Or for coil or for capacitor, resistivity depends on frequency. For capacitor, resistivity decrease on frequency because it is 1 over omega c. For coil, resistivity should increase on frequency. Here it is. For coil, resistivity increase on frequency because it is omega L. For power, also without consumption, the instantaneous power is sinusoidal function, but if we will integrate this power to obtain the total one, the average value for period, it also will be 0 without any consumption. That is why we obtain the comparison table of all our 3 elements, resistor, coil, and capacitor, with the main properties, with the main characteristics. For resistor, current, Ohm law. For coil, current is an integral because voltage is a derivative, and if we want to find current, it will be opposite function, opposite operator, and it will be the integral function. For capacitor, current is a derivative. Voltage from this Ohm law, just from the ratio, we could find it. For coil, it is derivative. For capacitor, it is integral because current is a derivative. If current for capacitor is derivative, then voltage for capacitor is integral function. The power equation, instantaneous power as Joule heating, where current will be sinusoidal. For coil and capacitor, multiplication of current on voltage. Or we substitute instead voltage this derivative, or we substitute instead of current this derivative. That is why the total energy that we have for resistor, it will be integration of Joule heating for the period of time. And for just one moment. And for coil and capacitor, it will be a general formula as inductivity on square of current or capacitance on square of voltage. It is energy that stored inside electromagnetic field. Inside electromagnetic field, we obtain this energy depending on the level of magnetic field, because our coil and our capacitor are storages for energy inside the circles. Just a comparison table for the main properties. Then let's moving forward. We told that all basic laws, they stay true. It is so. You could use Kirchhoff current law for complex numbers. You could use Kirchhoff voltage law also for complex numbers. You could use current Kirchhoff law for any moment of time if you have couple of branches. In each branch you have sinusoidal current, and you want to use current Kirchhoff law. Then, or you could use them as time function, as sinusoidal values. And in any point of time, for this sinusoidal function, you could write the Kirchhoff law and it will stay true. For instantaneous values and functions, we are pointing as small letter. Or you could use vectors. You could use vectors in complex form. Vector is a constant value, and that is why we point it as a capital letter. It also will be true in any form that you want, or as a time function in some point of time, or as vector, as root mean square value, as effective value of this sinusoidal function. You could use this Ohm law, Kirchhoff law. Here is a representation, or in sinusoidal adding for couple of currents. You could use them as time function, or in complex numbers. Here is a representation in complex vectors in complex numbers, where vector represent the effective value of this sinusoid. The same for voltage law. For any circle, you could add all voltages inside it. Voltage will be in three forms. First form will be for resistors. Second form will be for coils. The last form will be for capacitors. Three types of voltages. You are adding them all together and obtain the voltage of electromotive force. It is when you are using sinusoidal functions. For this situation, you will obtain or differential equation or integral equation for sinusoidal function. It is quite complex mathematics. That is why we are using complex vectors. You could represent these three types of voltages as complex vectors, and using the such called impedance or total resistivity of all three types of elements. Here, for some example, in the form of sinusoidal function, For 3 sources, you have E1, E2, E4, adding depending on the direction. For 3 resistors, you have Ohm law, IR, 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 also depending on the direction. For 2 coils, you have 2 derivatives. And for capacitor, you have integral function. That is why instead of such complex equation, much simpler to use complex number. Instead of it, electromotive forces stays will be as 3 complex vectors, the same signs, but just in the form of vectors. For resistors, it also became complex vector on resistivity, 1, 2, and 3. For coils, instead of derivatives, it will be complex resistivity J omega L, multiply on current in both situations. For capacitor, instead of integral function, you have 1 over omega C complex resistivity for capacitor. And it will be your second Kirchhoff law or Kirchhoff law for voltages. Then you could add all resistivities all together, simplify this equation, and start to find the solution. That is just a general approach. How it is implemented in real life, we could look through the serial and parallel connection. Here is serial and here is parallel connection. As a general example of 3 main elements connection, because starting from this situation, we could determine the main property, the main characteristic of working mode of some branch. If you have single branch, how to find the property of this element. For the serial connection, we have 3 voltages. In total, it will be the general voltage on the points of branch. If you have couple of resistors or couple of coils or couple of capacitor, you just adding also all these voltages, and instead of any serial connection of one type element, you could point a total one. For example, if you have 2 resistors, you could add them as total resistivity. If you have 2 coils, you could add them as total inductance. The same for capacitors. If you have 2 capacitors, you could add them as total capacity using the complex resistivity of this element. Then in any case, after all simplification, as much element you have inside your branch, after all simplification, you will get only 3 main types. That gives you 3 main voltages. In general form, it will be just like that, but in form of complex vector, they transforms in this situation. In this situation, 12.1. Generally, you could substitute sinusoidal values instead of currents. From derivative, obtain shifting on plus 90. From integral function, obtain shifting on minus 90. Also, you will get omega L and 1 omega C before the equation. And once more, you will get the resistivity of resistor just as R, the resistivity of coil as omega L, and resistivity of capacitor as 1 over omega C. This resistivity, it stays true only for sinusoidal value. It is quite important moment. Just pay attention that all that we're speaking for, it is only for sinusoidal current. If your current will not be sinusoid, if it will be other alternating current, for example, exponential or non-sinusoidal with some disturbances, this mathematics will not work. It works only for sinusoid. But for sinusoid values, we could substitute instead of this general formula complex vectors. It will be 3 types of complex resistance, 3 types of complex vector, and we could add them all together. Complex resistance in 3 form, in the form of R, omega L, JXL and minus JXC. We named as complex impedance the total resistivity. And it will be vector with some length and some angle. And this angle, it determines only by resistivity of your elements. It will be, okay, let's show it here. On the real x of real number, you have R. On imaginary x of imaginary number, you have your x, XL minus XC. And the impedance vector, it will be hypotenuse for this triangle. 90 degrees angle, initial phase of your impedance, and the impedance will be hypotenuse inside this triangle. That is why you could use the Pythagoras theorem to deal with these 3 types of resistances. You could find impedance using the Pythagoras theorem, and you could find the angle using the arctangent function. I think more detail we will speak about it the next time. Why it is important? Because when you are looking on the angle, when you are measuring angle of some branch in system, it gives you information which type of system do you have, which type of resistor, coils, and capacitor do you have inside your system. That is why it's quite important information, and it could be get from the angle measurement. But I think we will return for it next time. We'll discuss the vector forms. Also, we will move for parallel connection and also discuss vector form for parallel connection, where it is, just one moment. For example, here. And then after these vector forms, we will move for power describing, because power will be also complex numbers. Complex numbers with real part and imaginary part. But it will be next time. For now, maybe you have any questions. Maybe you want to ask something about the material. Please welcome. Everything is okay?
For now, yes.
Okay, okay, perfect. Then is everything okay? For now, that's all. Thank you for your attention and wish you a nice day. See you next time on the next week. And once more, a nice day. Goodbye.
Okay, have a nice day.